So we have already discussed up to the magnetic moment and magnetic force held by a current carrying wire in a magnetic field. Now we will move on to another case of the magnetic field calculation, which can be done easily by Ampere circular law, that is the calculation of the magnetic field by solenoid. So for the entire solenoid we will not derive the result, but we will mention some points which are required for understanding the magnetic field of the solenoid. See, if there is a hollow insulating cylindrical pipe and copper wire is wound around this pipe and current is flowing through this. Current is flowing through this. Then each turn of this copper wire will behave like a loop, current carrying loop, and as a result it will produce the magnetic field. When there are many loops, suppose there are n number of loops, and then for each loop behaving magnetic field, it will produce a resultant magnetic field, and that is the magnetic field of the solenoid. Now each loop is behaving like a bar magnet, we know. Now in this loop, in which direction current flows? Finally like this. So in a particular loop, what is the direction of the magnetic direction of the current? Is it clockwise or going anti-clockwise? If you observe from this side, your eye is here and you are looking towards this pipe, and in each loop you will find that the current is going clockwise. Current is going clockwise like this. Clockwise means towards your eye, from where you are looking, you feel that it is clockwise. Towards your eye there is a presence of the south pole. And if you see from a motion and you feel that the current is going anti-clockwise, then near to your eye there is a north pole. So here near to your eye there is a south pole. Now what happens in this case? This first loop is just behaving like a bar magnet, such that one south pole is produced here and one north pole will be produced here. So this first loop is behaving just like a bar magnet. We can consider this like bar magnet. Next loop is also behaving like bar magnet in a similar way. So south is there, north is there. Next loop is also behaving like bar magnet. That is south, north. Next loop behaving like bar magnet. There is south, there is north. So what happens overall? In the region midway, these two poles will cancel each other, these two will cancel each other, these two will cancel each other. So where the pole strength will not be cancelled, only near the two ends. That's why for the solenoid, poles are found to be towards the ends. Towards the ends. Similar to a bar magnet. Because in case of a bar magnet, pole present towards two ends, not at the middle. So this is the same reason. That's why bar magnets and solenoids or current carrying loops, magnetic fields are identical in shape. So in between, north and south overlaps, so they will cancel each other, but towards the ends, north and south will remain not cancelled. So they will represent a net magnetic pole strength on the two sides, slightly inside. Why? Because if you draw the field lines for this solenoid, this is just like a bar magnet and it looks like this. Inside the magnet, field is going inside the magnet, field actually goes from south, field line goes from south to north. Outside the magnet, its direction is from north to south, like this. So you can consider that from this point, the field lines are actually diverging out, because that is the position of the pole. This is the point at which the field lines are converging. So we can consider that the poles are placed slightly inside the solenoid, similar to a bar magnet, that poles are not at the geometric ends. It is slightly inside. Okay, because pole is the region from which the field lines either diverge or they will converge. From the north pole, field lines will diverge. From the south pole, field lines will converge. At the south pole, field lines will converge. Now see the middle portion of the solenoid. Almost this portion, these two, this point and this point, between the two poles actually. Okay, so pole is slightly inside, and see the structure inside these two poles. Field lines are almost parallel to each other. Okay, so inside the core of the solenoid, since the field lines are parallel to each other, and uniform magnetic field will be developed inside the core. But just outside, the field is not uniform because the lines are diverging, they are not parallel. At this point, the field lines are converging, so they are not parallel. So field is not uniform at these two ends, but between the solenoids, between these two poles, fields are completely parallel to each other, that is uniform field. Field lines parallel means field is uniform. Similar to a bar magnet. In the bar magnet, between the bar magnet, field is uniform. Between the two poles, field is uniform. But just outside the poles, field is not uniform. And that uniform magnetic field inside is directed along this, because drawing tangent at any point will give you the direction of that field, and that field is determined by mu naught n by L into I, where L is the number of turns of the solenoid and L is the length of the two poles, length between two poles. So we can write this one as mu naught in I, where small n is defined as turns per unit length, number of turns per unit length. So this is the pole in a region inside. This is the field in a region inside the poles, not just outside the pole. Outside the pole, field is not uniform, and we cannot calculate by this elementary method. This calculation was actually done by Ampere's orbital theorem, but outside the poles, you cannot apply Ampere's orbital theorem because there is a lack of symmetry. But inside the poles, the field lines are symmetric, means they are parallel to each other. So you can find the field as B equal to mu naught in I by applying Ampere's law. Okay. Now, this is the one case that we have to consider, and another case is that the toroidal shaped magnet. Toroidal shaped magnet means if this pipe is bent like this, so this shape is called a toroid. And in a similar way, if you pull this wire and through this wire current is passing, then inside this pipe a strong magnetic field will be developed, whose expression is similar to this one. But in that case, B can be written as mu naught n by, now the total length, it can be written in terms of the radius, that is 2 pi r. So again finally you can write mu naught n times I. Only the length is now circular, so it can be calculated from the result of the circumference. That is 2 pi r. That one is called a solenoid, this one is called a toroid. Basically same thing. So for the toroid, radius is given, don't get confused, because from that you can calculate 2 pi r, which is actually the length. Then n by 2 pi r will give you small n, and just put mu naught ni and you can find the field for the toroid. Okay. Now, after this, there is a chapter of magnetism in material. Magnetism of the material, but we will not discuss that chapter right now because that is mostly depending on the informative chapter. Not that much concept and mathematical calculations are not involved there, because that is much more easy than this topic. You can direct on your own read this chapter once, and then if there is any difficulty in understanding that ferromagnetism and all these things, I don't think there will be too much difficulty in understanding that, because it is mostly a theoretical chapter, not that much calculations are required. I will discuss the other chapter of the electricity and magnetism topic, which are more conceptual and requires much more calculations and mathematics. That is, one topic is electromagnetic induction. Another is the alternating current. So we will discuss these two first. First one is electromagnetic induction. What is electromagnetic induction? It is just the opposite effect which was observed first time by Ørsted. What Ørsted did in his experiment, there is a current carrying wire, and around the current carrying wire Ørsted placed a compass needle, and this compass needle is showing deflection. Means compass needle when shows deflection, if there is a magnetic field. So around the wire, if a magnetic field is produced, then only this magnetic field will affect the magnet of the compass, and as a result compass needle will deflect. So that is called the magnetic effect of the current. Means whenever there is a current flow, there is a magnetic field developed. Now, current, what do we mean by current flow? Current flow means charge is moving. Charge moving means around a charge electrical field will be produced. We know if there is a static charge, around the static charge electrical field will be produced. Now we can consider if the charge is in motion, then this field is no more electrical field. So this field is varying with time. So time variation of the electric field can actually produce a magnetic field. That was observed actually by Ørsted. Because time varying charge is moving, like a current means moving charge. Moving charge means electric field of the charge is varying with time at a position. Okay. Now, this time variation of the electric field produces a magnetic field, and that's why the compass needle will deflect. This was observed by Faraday. Now, the natural question comes, if the time varying electric field can produce magnetic field, then can the reverse is true, that can a time varying magnetic field produce an electric field? Can a time varying magnetic field produce an electric field? That was observed first time by Michael Faraday in his experiment, and later discovered, later named it as electromagnetic induction. Means in that case, actually a time varying magnetic field or a varying magnetic field is produced. This magnetic field is able to induce a current or induce an electric field into a material coil, into a conducting coil, and as a result current will flow through that conductor. Previously, magnetic field producing current produces magnetic field. Now magnetic field produces current. This is just the opposite effect of posted experiment. Now what Faraday did, first he considered this kind of coil. There is a galvanometer. Okay, galvanometer is perfectly at 0. Now consider a bar magnet. North pole, south pole. So Faraday put this bar magnet in front of this coil at a certain distance from the coil, and observe that if there is a deflection in galvanometer or not. And it shows that as long as the bar magnet is at rest with respect to the coil, there will be no deflection in galvanometer. Means no current is induced. Now Faraday start to move this bar magnet towards this coil. As soon as the bar magnet starts moving towards the stationary coil, you will notice that there is a deflection in the galvanometer. Means some current flows through the galvanometer. Suppose the deflection is on the right side. Deflection is on the right side. Means current flows. Now Faraday increases the velocity of the bar magnet towards the coil. So bar magnet is now moving towards the coil with some acceleration. And since it is moving faster, Faraday noticed that this deflection is much more, means the value of the current will increase. So if it is going slowly, then there is a value of current. If it is going faster, the value of the current will increase and deflection will be more. Clear? Now, Faraday take this magnet inside these turns without touching the magnet to the turns. If there is too many space and magnet is placed inside, and Faraday noticed that as soon as if the magnet is inside the turns, if the magnet stops, immediately the current goes to 0. There will be no deflection. Means the closeness of the bar magnet and the coil cannot induce any current in the coil. It is only the relative motion between the magnet and the coil that can only induce the current in the coil. It may be so close inside the loops but stops. They at rest, there will be no current. Clear? Now Faraday consider that if this north pole is taken away, Faraday sees that there is again a current. As the bar magnet is moving now away, previously north pole is moving towards the coil, now the north pole is taken away from the coil, again there is a current, but the deflection is in the opposite direction. Same as that of previous cases, but in opposite direction. If it is moving slowly away, then current is small. If it is moving with a high velocity, then current is large. But in the opposite direction. Okay. Now, Faraday changed the setup. Means, now instead of bringing the north pole, he considered that south pole is there and north pole is there and it is coming. what happens? When the north pole is moving towards the coil, the deflection is on the right. Now when south pole is coming, the deflection flows on the left. And when south pole is going, the deflection is shown on the right. Just opposite. If you change the polarity, then there is a change in the direction of the current flow. If you change the direction of motion, then there is also a change in the direction of current flow. So two factor effects. Write down. Faraday experimentally observed that if the direction of motion of a particular pole, if the direction of motion of a particular pole towards the coil is reversed, the direction of current induced in the coil will also reverse. Okay. Direction of motion of the current in the coil will also reverse. Faraday experimentally observed that if the direction of movement of the pole towards the coil is reversed, Faraday experimentally observed that if the direction of the motion of a particular pole, direction of motion of a particular pole is reversed, the direction of motion of the current is also reversed. Means pole, a north pole going, north pole moving in. The direction of current in two places will be opposite. Now, if the pole is changed, then the direction of current is also reversed. Instead of north pole moving, now it is south pole moving, still the current will be reversed. Okay, so 2 points are there. First point, for a particular pole, if the direction is reversed, then current is reversed. Now, taking the same pole moving towards the coil or away from the coil, suppose towards the coil, either north pole can go or south pole can go. In these two cases, the direction of current will be reversed, opposite to each other. Now, Faraday experimentally observed this. So, first thing that we can say that the current induced in the coil, why a current flows through a conductor? Because there is an EMF developed, and this EMF developed will send the current through the conductor. So I can consider that there is an EMF induced when there is a change in magnetic field B. Because poles are moving close, means magnetic field associated with the coil will increase. Pole going away means magnetic field associated with the coil will decrease. Because from these poles you can consider actually field lines are coming. So as the pole is closed, more and more field lines are passing through the coil. That means the number of field lines associated with the coil will increase. And when it is going away, number of field lines associated with the coil will decrease, and that induces the current. Okay, so number of field lines associated with the coils must be changed, because if you take the magnet at rest, then number of field lines passing through the coil will not change. Only it will change if you move the bar magnet towards the coil or away from the coil. Then only current will be induced. So first factor is that it depends on B. So if B changes, then E will also change. Clear? First point. Next, instead of moving the bar magnet, if I move the coil towards the bar magnet or away from the bar magnet, the same situation occurs. Because relative motion is important. Who is moving towards whom? That is not important. Bar magnet can move towards the coil, coil can move towards the bar magnet, nothing, no change. But relative motion must be there. If you consider that bar magnet and coil both are moving around the same direction with constant velocity, no current will be induced, because with respect to the coil, bar magnet has no motion in that case. So bar magnet has to be moved. There should be some relative motion of the bar magnet with respect to the coil such that an EMF is induced in the coil. Okay, so write down this point. In Faraday's experiment, it was observed that for an induced EMF to build in the coil, relative motion between coil and bar magnet, is necessary. Relative motion between coil and bar magnet is necessary. This was first detected by Faraday. Okay. Now, the second. Faraday also observed that instead of moving the bar magnet relating to the coil, if both are kept fixed and I change the area of each turn of the coil, area of each turn is elongated and then decreased, or the increased or decreased area. Okay. Then also current is induced and galvanometer showed deflection. So write down the second point. Faraday noticed, area of each turn of the coil is changing, there is again an induced current in the coil. Means without relative motion between bar magnet and coil, you can change the area. Still, current is induced. Okay. Next. See, if Faraday changes the number of turns of the coil, then also current will be induced. Because number of turns change means area will actually change. Previously, 4 turns will include some area. Now if I do 8 turns, then area of each turn will be increased. And if I take 2 turns, then I can consider that the area is increasing. So actually if the number of turns increases, that means there is a change in area. Clear? Now, the next point, third one. Faraday also observed that if this coil is rotated about its axis, if the coil rotates about its axis in presence of the magnetic field, and EMF is also it is an EMF is induced in the coil. Means again current flow will be there. Check. This is the diagram. If the coil is rotated like this, then there is an EMF induced in the coil and current will flow through the coil. Okay. Now, after all such observation, I can say that this EMF depends on V, this EMF depends on changing area, this EMF depends on changing direction. That is the due to rotation. What happens? If the magnetic field is like this and area vector is like this, or area vector can rotate like this, so angle between the magnetic field lines and area vector is changing. So let us consider that angle to be theta, and it is also depending on another factor, that is n, number of turns. So all this clearly shows that magnetic EMF induced is actually depending on a change of a quantity which is composed of these four factors. Which quantity is composed of these four factors? Magnetic flux. So we can define the magnetic flux phi, that is MPa. MPa. Now another term should be there, NBA cos theta. NBA cos theta, because flux is defined by dot product B dot ds. So I consider the area to be A, so it is B dot A. So n terms are there, so it will be NB dot A, means NBA cos theta. So this changes means there is a flux, there is an EMF induced. So E can be written as by Faraday as directly proportional to d phi dt. E is proportional to d phi dt. This was also experimentally observed by Faraday by measuring the deflection of the galvanometer. Means if either of this quantity increases, flux will, either of this quantity changes, the flux will change. Flux will change, and as a result EMF induced will change. So by measuring the whether the induced EMF is increased or decreased, Faraday comes to a conclusion that if the magnetic, if there is a change in magnetic flux associated with the coil, and EMF is induced in the coil, and this EMF is directly proportional to the rate of change of magnetic flux. Okay, so Faraday's first law is just an observation. It says that if there is a change in magnetic flux linked with a coil, and EMF is induced in the coil. Just an observation. Second law gives you certain mathematical form, that is EMF induced is directly proportional to the rate of change of magnetic flux linked with the coil, that is d phi dt. Now, what about the direction? What about the direction of this flux, direction of the induced current? Okay. That can be determined by another law called the Lenz's law, which is consistent with the conservation of energy. And the law says that induced current will flow in the coil in a direction so that it can oppose the cause of its production. Okay? So first write down the Lenz's law. Lenz's law. It says induced current in a coil will flow in a direction. Induced current in a coil will flow in a direction so that can oppose the cause of its production. Cause of its production. Okay? Now, we will demonstrate this portion a little bit. How it comes. See. Consider north pole is moving and as a result current will be induced. Now in which direction current will be induced? Will the current flow in this way or will the current flow in this conductor in this direction? In which direction? What will be the direction of the induced current? Will it be denoted by this red mark, that is clockwise, or will it be denoted by this green mark, blue mark, anti-clockwise? Why? Why anti-clock? See, if it moves anti-clockwise, then in this loop the current is going anti-clock. If you observe from here, then on this side which pole will be produced? North. And on this side which pole will be produced? South. So this north pole will repel this north pole and try to oppose this motion. So what is the cause of this induced EMF? The movement of the bar magnet's north pole towards the coil. Now induced current, it produces north pole on the same side, then it can oppose the cause of its own production. That is Lenz's law. Now for the moment, just consider if the converse of Lenz's law is true. That is, current will move in this coil in this way, violating Lenz's law. Then what will happen? South pole will be produced here and north pole will be produced here. Then what will be the net effect? This south pole will attract the north pole of the bar magnet. As a result, bar magnet will be attracted towards the coil, means its motion is accelerated. Its motion is accelerated, and accelerated motion means velocity is increasing. So the induced EMF will increase and current in the coil will increase. That is very beneficial for us, but it is not possible. So it is very beneficial for us. Like that, if you switch on the circuit and then disconnect, the bulb will go on forever. Circuit on its own produces the energy, electrical energy, to blow the bulb. That is very beneficial for us. We don't have to pay the electric bills, but it is not possible because circuit on its own cannot produce its electrical energy to run the devices. Okay, so you have to supply any other form of energy. Now what happens? If south pole is there, that is opposite of Lenz's law is true. You can consider that once you push the bar magnet little bit, there is a current flow, and as a result, south pole is produced here, and it will attract the north pole. So bar magnet is accelerating towards the coil. So induced current in the coil is increasing, and bar magnet's motion towards the coil will be increased much more. Means electrical energy is continuously produced in the coil, but no other form of energy is given. So that is the production of electrical energy without any other form of energy converted to the electrical. That is a violation of the conservation of energy. Because conservation of energy says that energy cannot be created, cannot be destroyed. So in this way, if opposite of Lenz law is true, we can say that coil on its own can produce the electrical energy, can create the electrical energy, which is a violation of the conservation of energy. So this is not true. So what is true? The opposite of that. That is Lenz law. Now, how Lenz law will explain this conservation of energy? North pole will be produced here. So north pole will repel the north pole of the bar magnet. So bar magnet motion is retarded. So this induced current try to stop the bar magnet. Okay. Then to maintain the current in the coil, what do you have to do? You have to push the bar magnet towards the coil against that force, that repulsive force. Means you have to do mechanical work, and then that mechanical work will push the bar magnet towards the coil, and current in the coil is maintained. Current in the coil is maintained if you push the bar magnet towards the coil. Means you have to supply mechanical energy. That mechanical energy is converted to electrical energy, and current will run through the coil. Okay. So opposite of Lenz law is a violation of the conservation of energy, because in that case you have to consider that electrical energy can be created by the coil itself without any battery or without any other form of energy, which is not true. Conservation of energy is a fundamental principle, it cannot be violated. So what you have to do, the coil, due to this property of the Lenz law, will actually oppose the bar magnet, because bar magnet's motion, north pole's motion towards the coil is actually responsible for this induced current. So coil will try to stop this motion, because Lenz law is hampering the origin. So coil will try to stop this motion by repulsive force produced by the north pole. Then against that repulsion, you have to push the bar magnet towards the coil, such that current in the coil can be present, cannot destroy itself. Means while you are supplying mechanical energy, that energy will be converted to the electrical energy. Okay, without any other form of energy, you can never produce electrical energy. No coil can do it. So conservation of energy is the main underlying principle behind Lenz law. So write this point. Lenz law is based on conservation of mechanical energy, conservation of energy. Lenz law is based on conservation of energy. So together with Lenz law and Faraday's law, taking together, I can write now E equal to minus, this minus sign comes from the Lenz law, because it opposes the movement. d phi dt. E equal to minus d phi dt. Okay. The proportionality constant is taken as 1, and this minus sign shows that the Lenz law is true, and induced current will oppose the cause of its production. So due to flux change, induced current is produced. So induced current will try to stop this flux change. Okay. Now, if I put all the quantities containing in phi in this expression, minus dVt of n b a cos theta. Okay. n b a cos theta. If I put, then I can write this one as minus n e cos theta ddt minus NB cos theta ddt minus N minus dA cos theta dN dt minus NBA ddt of cos theta. So this one is actually each term by using the product rule. So whenever you are doing the derivative with the product rule, when you are taking derivative of one, other functions taken as constant. So first one, I take derivative of b with respect to time, then other function constant, that is NA cos theta ddt, then minus NB cos theta ddt, then I consider BA cos theta ddt minus NBA ddt of cos theta. Now I can consider that if this first one is present only, then there is a change in the induced, then there is an induced EMF in the coil, because changing B changes produces an induced EMF. Clear? If the magnetic field associated with the coil will change, EMF will be induced. Instead of magnetic field, if I consider A, B, theta all are constant, but A is changing, there is an induced EMF in the coil. This term shows that if there NB cos theta, BA cos theta constant, and only number of turns changes, there is also a changing in the flux, and as a result there is an induced EMF. So all such changes can induce an EMF in a coil. Changing B can induce, changing A can induce, changing N can induce, and changing theta can induce. Okay. Now check this down carefully. In all other cases, theta are constant. Here theta constant, here theta is constant, here theta is constant. Okay. So this, in this case, theta is not constant. So what it gives? Derivative will give minus cos theta d theta dt. D theta dt is omega, angular speed. D theta dt is omega, which I draw in the previous diagram. That omega. Okay. Now, one more crucial. This is taken as theta equal to omega t. Omega equal to theta by t. So theta equal to omega t. Now see this, what this final, this quantity gives. I will discuss this quantity a little bit. So it will produce a part in EMF. So write it E4. So this first part is taken as E1, second part E2, then E3. Then I consider this one is E4. So E4 will become, check, NBA sin theta d theta dt, because cos theta derivative will be minus sin theta, so this minus will go on. So it will be NBA sin theta d theta dt. Now d theta dt is omega, so we can write this one as NBA omega into sin. Theta can be written as omega t. theta can be written as omega t. So what we get, this E4 equal to, I can consider NBA omega is the maximum value of this E4, because when sin theta is giving 1, then it will give you the maximum value. So maximum value can be written as suppose E0. So it is produce an EMF which is varying with time, sinusoidal. This E4 part is producing an EMF which is varying with time, sinusoidal. Because in all three previous cases, E1, E2, E3, this theta is constant, but in the fourth case, theta is variable. So this T is variable, so this is giving a sinusoidal EMF, means alternating voltage. This one is giving an alternating voltage, and current sent by this part of E4 is an alternating current. Okay, so in all the first three cases, when P changes, when A changes, when N changes, it will induce a direct current. But when the rotation is there, that is the angle between P vector and A vector is changing, it will induce an alternating current in the circuit. So from this Faraday's law, we can directly go to the study of the alternating current, because alternating voltage can be generated in this way. By rotating a coil in a magnetic field, you can generate the alternating voltage. And if that voltage or EMF is applied to a circuit, then that circuit is driven by alternating voltage, so called the AC circuit. Okay? Now, next, we will discuss one or two problems on Faraday's law. Suppose flux is given, and magnetic flux associated to a circuit is given by T square e to the power minus T. This function is given T square e to the power minus T. It is varying with time. It has the proper unit of flux. We consider T square e to the power minus T. So, keep track of the proper unit. I should write here one constant, because otherwise it may happen that apart from this constant you cannot put a dimensionally correct. So you can consider a constant there. Some constant K is phi equal to some constant K into the T square into e to the power minus T. Now, find the finite time, find the finite value of time after which the induced current in the circuit, will be zero. Means initially it is zero, then after finite time it will be again zero. Then what will be the value of that finite time when that induced EMF current in the circuit will be zero again? That you have to find out. This is the expression for magnetic flux linked with the circuit. And since it is time dependent, means there is a variation of the flux with time, then initially the induced current is zero, then after some time induced current will be again zero. So that time has to be found out. is the answer. Correct. See, from this first you have to calculate d phi dt using the product rule of derivative. So derivative of this k is a constant. Now, first take the derivative of the first function. It will be 2t. Second function is multiplied with it. Then first function remains same. Derivative of the second function. Derivative of the second function means minus e to the power minus t. Okay. Now from Faraday's law we know that E equal to minus d phi dt. And if current is 0, then EMF should be 0. Then I can put here directly 0 and say that d phi dt is also 0. Then from that equation just put it will be a 2t common, e to the power minus t common. K is already divided by 0 will become 0, so we will not bother with that. Then first term it is 2 minus t will be 0. Then three values of t will come from this equation. One is t equal to 0, another is t equal to 2 seconds, another is t tends to infinity. So which one is the correct answer for this problem? This one. Because t equal to 0 means when the EMF is not at all given, flux is not at all changing, t equal to 0 means. So at that point it is already 0, there is nothing. So that is not the finite time after which EMF will be 0. And t tends to infinity, EMF will be 0, that is also not the finite value. So what is the finite time after which EMF will become 0? That is 2 seconds. Okay. Now, next after this Faraday's law and introductory part, we will introduce a concept of motional EMF. That is another part of this topic, which is very important, which can be introduced by using Faraday's law, or even without introducing Faraday's law we can explain the origin of the motional EMF. First, I will explain the origin of the motional EMF without using Faraday's law. Then we will introduce the origin of the motional EMF by using Faraday's law. First, I consider an example. This is P side, this is Q side of this wire. This is a rod, metallic rod, conducting rod. And this one is considered as the x-axis, this one is y-axis, this one is z-axis, and we consider a uniform magnetic field is present in along along z direction, that is denoted by B equal to magnitude V into K cap, and this rod is moving with a constant velocity along the y direction, denoted by V equal to V K cap, sorry, V J cap. Okay. So the rod is placed in such a way that length of the rod is parallel to x-axis. Length of the rod is parallel to x-axis. The rod is moving in y direction with a constant velocity v, and magnetic field is present in the z direction b. Okay. So there are, I can consider, since it is a metallic rod, there are many free electrons in the metallic rod, and each electron is now moving in the magnetic field, so they will experience some magnetic force. So I want to find the magnetic force on an electron. That can be written as Fm equal to magnetic force means Q into V cross B. For electron, Q is minus E. Now V cross B. V cross B means Vp. J cross K. V cross B, the expression for V and B is substituted. So it will be minus EVB into unit vectors are J cross K. So what is J cross K? J cross K? I plus I. J cross K will be plus I, cross product, not dot product. So it will give us minus EVB I cap. So the magnitude of the force is EVB and direction is along negative x-axis. Direction is along negative x-axis. Okay. Now I can show you that this electron is here and it is giving a magnetic force along this direction of negative x-axis. Fm. Okay. Electron is giving a force along negative x-axis. So in which direction electron will move and accumulate? At which point? At the point P of the rod. Because electrons are feeling a force on that direction. So electron will move on that direction and it will be accumulated there. Okay. Then once the electrons are accumulated near point P, so not only an electron goes, I consider only one electron, but there are many electrons in the conductor. Large number of electrons in the conductor because we consider metallic conductor. So electrons are going towards this point. So I consider it negative, 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 negative. So there is an accumulation of the negative charge. There is an accumulation of negative charge, that is electron, near the point P. So P side is now of the rod is now negatively charged, we can consider. Then overall, what is the total charge initially for the metallic conductor? 0. Because there is no excess electron in a metallic conductor. The free electrons are there, but they are free from only to move within the material. So total charge will become 0. So now if the charges are moving one side, negative charges are moving to that P side, apparently the Q side will become positively charged, but that should be of equal amount. So if the P side contains minus Q 10 coulomb charge, Q side must contain plus 10 coulomb charge, because overall the conductor should be neutral. Okay. So on the N side there is a, we can consider the remaining ions will be on this side, and this one will become positively charged. Okay. Now once the charges, negative charges are settled at point P, positive charges are settled at point Q, then these charges can be considered like a static charge. Static charge will produce an electric field. In which direction? From the negative charge to the positive charge, or from positive charge to the negative charge. From positive to negative. The electric field will be set up by these charges from the positive charge to the negative charge. And what is the direction of that field? Along this. So that field can be written as E equal to magnitude of E into positive to negative means minus I cap. From Q to P, this field is set up. So Q to P means direction along negative x-axis. So I consider it is minus E I cap. Now this electron will also feel some electrical force. Previously it is only feeling magnetic force, but now since the electric field is set up, this electric field will also apply the force of the electron. Then what is the force of the electron? Fe, electrical, that is minus E into electric field. That is Q into E, that is minus E into E. But E is already having a minus sign, so it will become plus E I cap. This one is not a vector. So I can draw this force on the electron also. That is Fe. Now see, Fm and Fe are opposing each other. Fm and Fe on the electron are opposing each other. Now consider a situation. Initially, there will be no electron on this side, so there will be no positive charge on this side. So as one by one electron is transferred to terminal P, the positive charge will build up at terminal Q. So this electric field is continuously increasing. So as more and more charges are transferred to Q, the electric field will increase its magnitude. So one time will come when this electric field will balance, the electric force will be equal to the magnetic force of the electron. Initially, magnetic force is present, but electric force was zero. Now, one by one electron is transferred to this point, and this point will become apparently positively charged, so the electric field grows. So suppose initially minus 1 plus 1, then minus 2 plus 2, minus 3 plus 3, minus 10 plus 10, minus 20 plus 20. So the electric field grows. So one electric field will grow, this electric force will be stronger. Then one time will come when this electric force will balance the magnetic force. At that point, I can write magnitude of Fe and magnitude of Fm will become equal when these two forces will balance each other. Correct? Now, what will be the velocity of the electron at that point when these two forces balances each other? When these two forces balances each other, what will be the velocity of the electron? Force 0 does not mean velocity 0 always. It may be velocity is constant. So what actually initially to the velocity of the electron? It is increasing from 0 and it is accelerating because of the magnetic force. Now electric force goes on increasing, means it will decrease the net force, and one time will come when net force will become 0. So electron will achieve the constant velocity. That is called the drift velocity that you have learned. Slowly it is increasing, and finally it will become constant. Like this. The velocity of the electron will follow this kind of a behavior. It is just like the terminal velocity in viscosity curve. V versus T. Remember, initially it is accelerating, but now the acceleration is decreasing because of the increasing viscous force. The same thing happens when the raindrop is falling. So its velocity downward is increasing because of the gravity, but as soon as velocity increases, the air friction will also increase. That is called the viscous force. And increasing air friction one time will balance the weight. And as a result, raindrop is falling with constant velocity. That is called the terminal velocity. The same thing happens. Initially, electrons are moving accelerating due to magnetic field, magnetic force. Then, due to the charge separation, electric field force is increasing. And one time will come when this increased electric force will balance the magnetic force, and electron will move with a constant velocity. That is, we have already calculated as drift velocity. But the origin we haven't discussed. Okay. Now, just equate the then what is the magnitude of F E into E? What is the magnitude of this Fm? Magnitude EV T. So from this one is a crucial expression from which you can find out the velocity of an electromagnetic wave. That is by dividing the magnitude of electric field to the magnitude by the magnitude of magnetic field. E by B will give you velocity of the electromagnetic wave. If you know the electromagnetic wave's amplitude, and if you know the magnetic wave, if you know the electric field vector's amplitude or magnetic field vector's amplitude, then dividing these two you can easily find the magnitude velocity of the electromagnetic wave. Okay. Now, we can consider the length of the conductor is L, suppose. Then this EMF E can be written, then this electric field E can be written as potential difference between two ends, potential difference that exists between two ends divided by length, because we have earlier seen that electric field equal to minus dV/dr. So in the calculation of the drift velocity, we have also used this point that potential difference by length is called is equal to the magnitude of the electric field. So let us consider potential difference between these two terminals is VQ minus Vp. This divided by L will give you L is the length of the conducting rod. So Vp minus Vq is the potential difference divided by L will give you field. Then that can be written as V into E then I can write this is equal to VLB. This potential difference Vp minus Vq, sorry, Vq minus Vp is equal to VLB. This one is capital V denoting potential. This one is small v denoting velocity. Now, what Vq minus Vp called potential difference between the two terminals of the rod. In which condition? Is there anything connection like this? Is there any connection like this? Not, this connection is not there. When this connection is made, this is called the closed circuit. When this connection is not made, it is called open circuit. So potential difference between the two terminals in open circuit is called potential difference between two terminals of a battery or cell in open circuit condition is called EMF. So that is actually the EMF. So this rod is behaving like a battery or cell. A metallic rod moving in a magnetic field will behaving like a cell, because across its two ends an EMF will be developed. Potential difference developed in open circuit condition, that is called EMF. If you join them with an external circuit having some resistance, then there will be some current flow. Okay, and see, this EMF is generated by due to the motion, because if you put V equal to 0, this EMF will be 0. Conductor at rest will not feel any, not produce any EMF inside the magnetic field. So due to the motion, this EMF is developed. That's why the name is motional EMF. Motional EMF. This one I derived from the elementary idea of magnetic force on a charged particle. In a magnetic field, an electric force on a charged particle in an electric field. From that idea, I derived this one, motional EMF. It can be derived much more easily by using Faraday's law. That's why Faraday's law is that much useful. It is mathematically rich. You can understand all the microscopic detail of the motion, but its calculation is too long, and conceptually you have to calculate all these vectors, all these things. But in the Faraday's law, you can bypass all such rigorous calculation and derive this result directly, but you will not get what is going at the microscopic level. Here we discuss the motion of the electron at the microscopic level, that this constant velocity of the electron is achieved, which is considered as peak velocity, and all these things. How the electron is achieving that terminal velocity. We have discussed all these things. But in Faraday's law, we will lose those details, but the calculation will be much more easier. See, this process is clear. This one, now it is much easy to use the Faraday's law. Check. In Faraday's law, in a similar manner, we will consider the same problem. I will consider this one is P, this one is Q, this one is T. Magnetic field is there. Now, this is your x-axis, this is your y-axis, this is your z-axis, and it is moving with a constant velocity along this way. Okay. So, in which direction the rod moves? In y direction. In y direction the rod moves with constant velocity. So I can consider another portion of the rod which is slightly away from this portion. Okay, so I can consider this rod is moved by a distance in time dt. How much distance the rod is moved in time dt? V dt. That is dy. This one is v dt. In y direction it moves with velocity v. In time t, then with this constant velocity, distance moved is v into et. Clear? In time, it is its constant velocity along y direction is v. So in time dt, it moves a distance vt. That is v into delta t. Now, what is the length of the rod you consider? L. This entire length. So this area is actually like this. This is VDT, this is L. So what is this area? Tell me. VDT into L. So I can write it is V L into V into DT. This area. TA. This entire area is considered as TA, which can be written as LV dt. Length into breadth that we have considered. Now, in which direction magnetic field is present? Perpendicular to this area. Check. This area is a direction above. Magnetic field is also above. Magnetic field is perpendicular to this area. This area is like this, and magnetic field is like this. So what is the angle between this area and magnetic field? Area vector and magnetic field. Not 90. It's 0 because area vector is perpendicular to the area. Okay. With this surface area, the magnetic field is going like this. So angle between them is 90. But area vector is denoted by cross product. So angle between area vector and magnetic field vector is now 0. So dot product cos 0 will come, cos 0 will be 1. So I can write that some magnetic flux will be passing through this area, and that is B L V dt. Okay, that is B L V dt. Magnetic flux means magnetic flux is d phi equal to B into dA cos theta. Cos 0 will come, cos 0 will be 1. So it will be simply BLV dt. When d phi dt is BLV, I can write d phi dt equal to BLV. The same expression that you derive by using the cross product, the same thing comes. I calculate only the magnitude, not the sign. So that's why I write d phi dt equal to, if I should write it here more. That is coming direct without that much of calculation. Only you have to consider the length L of the rod is moving at distance VDT in time t. Then in time dt, then new area is formed. So with that area, take a dot product of the magnetic field, you will get the magnetic flux. Then magnetic flux, rate of change of magnetic flux is EMF. So that is from Faraday's law. So no such vector calculation is, or no such cross product is required for finding the motional EMF. So that is the power of Faraday's law. Okay. So I demonstrate here both the methods, calculating the is motional EMF by elementary microscopic method by calculating the force on electrons, and by using the macroscopic method, that is the flux change by Faraday's law. You can use this one for the problem solving directly because that much detail is not required, but in discussing that the microscopic method, you will get that relation E equal to VV. That is an important relation to solve the problems in many cases. So remember, so read that method also, and whenever you prepare the note, write that derivation also. Okay. Okay. So take a small break. Then we will start the remaining portion of this chapter and alternative current also. So now we will discuss some other effects of this coil, in which induced EMF is developed, and how induced EMF will lead you to different situations. One of those effects are actually a self-opposing effects. That is called the self-induction technique. Suppose there is a coil which is connected with a battery and which is connected with a variable resistance. This is a variable resistance. This battery EMF is given. We consider battery carrying certain amount of current in the circuit. This EMF is given E. Now due to this, there should be a current going through this coil, and this coil setup is just like a solenoid, just like a solenoid. So a magnetic field will be produced inside this solenoid portion. So magnetic field inside will be like this. B equal to mu naught N I by M, and N is the length of this coil. Okay. So any coil can be considered as a solenoid. So in this setup, if their current is constant, the magnetic field developed inside is B, and that is mu naught capital N by L into I. Now, what is the direction of this magnetic field? That I can also find, because if you look at this first loop, it looks that current is going in clockwise sense. Current clockwise means on this side there is a north pole, sorry, there is a south pole, and on this side there is a north pole. If you are looking from this side, it shows that current in the first loop is going clockwise, means on this side there is a south pole, in the opposite side there is a north pole. So the magnetic field lines inside can be drawn like this. I will draw certain field lines, not all, only two. This. Okay. Now, if by using rheostat I will vary this current, what will happen? See, this magnetic field is passing through the area of turn of each turn of the coil. Suppose the coil has n number of turns, then the flux associated with this coil will be N B A, right? Flux associated with this coil or this field will be NBA. So if I put, then it will be mu naught N square by L into A into I. See, mu naught N square into A by L into I. Okay. Now think about this situation. If I change this current by varying the variable resistance is just like a rheostat or regulator. If I change the current, what will happen? There is a change in this flux, and you know that if there is a change in flux, then there is an induced EMF in the coil, and EMF is induced in the coil. So now we will discuss it one by one. Suppose I want to decrease this resistance, then what will happen? Current in the coil will increase, so flux will increase from this equation. See, B is increasing means flux will also increase. Then due to increase in flux means change in flux. Due to change in flux, and EMF will be induced, and from Faraday's law, this induced EMF will try to oppose the cause of its production. What is the cause of the production of induced EMF? Increase in current. So it try to decrease the current. If by decreasing this resistance I increase the current in the circuit, then flux will change, means flux will increase. Then EMF will be induced, but due to Lenz's law, this induced current has a property, induced EMF has a property to decrease its own to destroy its own effect. So what causes it? The increase in current. So it will try to decrease that current. So what it will do? If the current is increased, it will send another current in the opposite direction, producing an EMF. It will produce a current in the opposite direction, such that increased current will be decreased to the same value. Because initially suppose 10 ampere current flows, you change the resistance and suddenly the current increases to 12 ampere. So the induced EMF will be developed and it will send the current 2 ampere in the opposite direction, such that the net current in the circuit is again maintained to the 10 ampere. So it will not allow to 12. It will try to decrease it by sending a current in the opposite direction. The same situation occurs if you increase the resistance. Suppose 10 ampere is initially flowing, you increase the resistance, current drops to 8. So induced EMF immediately send the current 2 ampere in the same direction, such that it will become 8 plus 2, that is 10. So it will always try to restore the current in the circuit to the same value. Okay. So that means this induced current has a property to maintain the same current in the circuit. That's why this effect is called self-inductance. Means it will induce a current on its own to maintain the same current through it. This property is called self-induction. Self-induction. Okay. Suppose in his pocket there is 100 rupees. he has to maintain always 100 rupees in his pocket. I increase his, I give him 10 rupees. So in his pocket that amount of rupee will be 110, but he has a tendency to maintain 100. So he will remove another 10 rupees and put it outside. Similarly, if I take 10 rupees from him, he will collect 10 rupees from others and put in his pocket, such that to maintain the 100 rupees in his pocket always. This current has the same, this circuit has the same tendency. So if you try to increase the current in the coil, it will produce a back EMF, which will produce a current in the opposite direction to decrease it to the same value. If you decrease the current, it will try to increase the current by producing a current in the opposite direction. That's why this EMF induced due to the change in the current is called back EMF. Back EMF means it will generate the current in opposite direction to the increase or decrease, such that to restore the current in the constant value. Okay. This property is called self-induction. So write down. The property due to which a circuit opposes any change in current flowing through it is called self-induction effect. Self-induction effect means the circuit will induce current on itself to maintain the constant current through it, called the self-induction effect. And the strength of this self-induction effect for a circuit and the strength of the self-induction effect for a circuit is measured by strength of the self-induction effect for a circuit is measured by self-inductance, that is called self-inductance or coefficient of self-inductance. Because the effect is self-induction, effect is called self-induction. Its strength is measured by self-inductance or coefficient of self-inductance, that is considered as an L. So how can we derive this one? This quantity is the L. So I should not write this capital L. I should write this length as small l. Okay. Such that I can now write this quantity is L into I, where L is the coefficient of self-inductance. That is L equal for this coil solenoid will be mu naught n square A by L. And see, it is completely a geometrical factor. It does not depend on current. This strength is depending on the geometrical factor, that is number of turns, area of cross section, length, and external factor is only mu. Means if it is an air core solenoid, then there is mu naught. But if an iron rod is inserted inside the solenoid, then mu will increase, mu relative. Permeability changes, and as a result self-inductance will change, increase. Okay. Now, this property is just like a property of mass. Suppose if I apply a force on this small mass, then with a small force it can be moved. So this cannot oppose any effect of force strongly. But if I apply the same force on this table, will it move? No. So whose resistance to the force against force is more? This one, that is measured by its inertia. Mass is a measure of inertia. Similarly, self-inductance is a measure of the electrical nature of the circuit. Means any circuit will try to maintain the electrical state. Means constant current. If you try to change the current, the circuit will try to oppose. If you try to increase the current, it will oppose. If you try to decrease the current, it will also oppose. So this property is similar to inertia. That's why L is similar to mass. It is called electrical inertia of the circuit. This L, that is self-inductance coefficient, is called the electrical inertia of the circuit. Okay. Now, you can put this phi equal to Li form in the Faraday's law, and then Faraday's law will become of this form. E equal to minus L di dt. You can also derive self-inductance from this Faraday's law. Means I put this phi in Faraday's law. Faraday's law is minus d phi dt. So putting phi inside, phi will be L into I. L is a constant, so coming out, so it will be minus di dt. So it can be defined as induced EMF per unit change in current. Per unit rate of change of current. Induced EMF per unit rate of change of current. That is also a measure of self-inductance. Good morning. Okay. So now there are many effects of the self-induction. One or two effects we have to discuss. One is this one. This is the mark. Any device. Okay. Mostly this tube. This one is a variable resistor. This one is rheostat, I consider. And this one is sending a voltage V. And this one is R. So not this one. This one is E. EMF. And this one is N. Okay. Now, it sends a current. Now, this one is called an LR circuit. LR circuit driven by DC source. LR circuit driven by DC source. Now, how many of you know the internal structure of a normal tube, not this LED tube? Internal structure of the normal tube. Is there any filament inside the tube? No. What is there? Some gas, mostly mercury vapor, is filled inside the tube. Whenever those old tubes are broken, some gases and all these things are coming out. So there are mercury vapor and some inert gases. which will not react. Now, in these two tubes, there are, you have to fit this tube in the socket, adjust this in the socket to fit this tube. Now, in this tube, how it glows? Because once you give the current, supply the current, the circuit is not completed, because inside there is no conductor. In the bulb there is a filament, then filament heated up, and its heat energy is due to heat energy, it is actually converted to light energy, and it is when it is glowing. But there is no circuit complete. So how it will glow? See, in the oldest tube, if you see, you will see there is something, a small device which is connected in the frame of the tube. That is called the starter. So if you see any pendant or anything, or any occasion, there are many tube lights used. So when you put those, when you bring this tube and call the electrician will fit it at different places, and these are temporarily set up, because after the occasion they will remove it and take it. Okay. Now how they will start the tube? They will bring this small device which is called a starter. They will connect the starter in the first tube like this, connect it directly after switching, tube will go, then they remove it, take it to the second tube, third tube, fourth tube, and this way suppose 10 tubes are switched on. Then what is the functioning of that starter? Starter is actually producing a heat, completing the path actually. There are two paths now. One path is through the tube and another path is through the starter. Through the starter it is a conducting path, because starter means there is a complete connection of the copper wire. So in the conducting path current will flow. And since it is a conductor, huge current will flow. That will produce a huge voltage difference across the two ends of the tube also, because this starter is actually connected against the tube in parallel combination. There are two alternative parts, one through tube and one through this. They switched on, so initially it is giving a high voltage, it raises the voltage too much. Then with that huge voltage, what happens? Through the tube there is electrical discharge of the mercury vapor. That means the electrons of the mercury vapor, due to this huge voltage, is actually leaving their parent atom and can move inside this entire container of the tube. That is called a plasma state. Then this electron is going to the high energy state. Now they are going to the low energy state and releasing energy according to the Planck's equation, E equal to h nu, and that radiated energy you can see as the glow of the tube. Okay. Now there is another thing in those old tube frame. There is a box. Normally it is called choke coil. It is called choke coil, not choke. In Bengali it is called choke. Tube में choke खराब हो गया. Means eye of the tube is destroyed, not eye. The name is CHOKE, choke coil. Means a setup containing a huge L, high value of inductance. Coil is called a choke coil. Choke. Now, what do we mean by choking? Most of the time we say South Africa is a choking team. It goes to semi-final and then it cannot win. It cannot go to the final. South Africa, whenever in a cricket match, South Africa initially is playing very well. It seems that no one can beat South Africa, but when South Africa goes to semi-final or final, definitely South Africa will lose. So it is a choke. It means it is initially high, but one time will come when it will fail. So same thing happens to this tube, this coil. What is there? Suppose suddenly the voltage changes. If voltage increases, then if there is no coil, then entire voltage will pass through which? Against the tube, and it may happen that tube will be damaged. So to prevent the tube, this choke coil will be used, because when the voltage is increased means more current will flow, and as more current will flow due to large electrical inertia, L high means high inductance, so it will oppose that current so strongly. So if current tries to increase too much, due to producing back EMF, due to Lenz's law, it will decrease the current that much, such that constant current and constant voltage is maintained against the tube. So the tube is prevented on using this choke coil. So it will, if the current increases too much around this, then since it has high value of inductance, so it will oppose that change too much, and it can reduce it to the same value, such that same value can be transferred to the next circuit component, that is the tube, and in this way choke coil give a safety to the original electrical device. That's why it is this error circuit with high value of L is called choke coil setup. So whenever this type of setup is given and it is given that it is used as a choke coil and 4 options are given, you have to mark that which combination. L should be very high. L should be very high, because low value inductor coil cannot be used as a choke coil. Low value means inertia low. Electrical inertia low means it cannot oppose that much. So high value means it can oppose any significant change in current. Clear? Now, another effect is there, that is called mutual inductance. Have you ever seen the effect of mutual inductance in your home, in their home? I have seen the effect of mutual inductance. And one time was there in Kolkata, when due to this mutual inductance effect, no one understand, laymen are not understanding this is the effect of mutual inductance. They merely thought that the neighbors are doing all this injustice to them, and due to that, between two houses, there will be something like fighting situation will arise. No one is understanding that this is the effect, completely effect of mutual inductance. But nowadays it is removed completely. See, previously, now today you see that TV. That TV is LED TV. LED TV, smart TV, all these things. Previously we saw LCD TV. But previous to that, we have CRT TV, cathode ray tube. Means there is a screen. That TV is not that much thin and small. It is like this much size and is like this, just like a heavy box, heavy tube box. This is. So there is a CRT tube. CRT means cathode ray tube. So from this there is a setup through which cathode ray is coming. Cathode ray means one of the flow of the electron actually. This electron in the screen, then inside it is a fluorescent screen. So electron will strike that fluorosensitive screen, photosensitive screen, and then it will produce some image, and that image is seen. Suppose electrons are coming. Suppose you want to see the faces of Shah Rukh Khan. How you can see? Those electrons will strike at every portion and creating the image of the face of the Shah Rukh Khan. That we can see in the TV. Now, sometimes it is the electrons coming and striking. Now, if you bring a magnet very close to that CRT screen, what will happen? This magnet will apply effect of the electron. As a result, electron is deflected, and it may happen that Shah Rukh Khan's face is changed to something else. Means it is not the proper face of the Shah Rukh Khan. It is some distorted image will be produced on the screen. Now, we are used to this situation, and what happens? Suppose you are seeing some song or television or anything, mostly, and this fighting between the two people arises occurs only in the summertime, not in winter. Why? Because in the summertime, when you see something, suppose a cricket match or a TV or a movie, anything in the TV, suppose in the other house someone opens, or in your house you open fan, you open the ceiling fan. Once you open the ceiling fan, what is happening? Previously ceiling fan was, and whatever it happens, suppose you switched off your own fan, but the other people in the neighboring building are not wanting to switch off their fan. It is summer, so they are switching on their fan, and when they are at that time, suppose he do not see this movie, he will sleep and he will switch on the fan, and due to that effect, your home's TV will be affected. And as a result, there is too much fighting, blaming, and I cannot see anything. All these things happen. But nowadays, it is completely removed because LED is depending on different technology, so the magnetic field cannot affect the LED's signal. Now, it is the same thing. So, what is mutual induction? First, write down. The property due to which a circuit opposes the change in current in the other circuit. Opposes the change in current in the other circuit. Previously in the self-inductance, a circuit opposes change in current on its own. Now it also try to stop the change in current in the other. It will interfere in other circuit. Okay. Now, how? But before that, I will just ask you one question. Have you ever seen the self-induction effect? Mutual induction effect, that effect that I tell you, you haven't seen that, because this problem is removed long before your birth. I have seen it in 1991, 1992 in those days. This effect is there. But self-inductance you can see even in till date. You can see the self-inductance effect. Can you tell me where you see the self-induction effect? See, sometimes when we switch off this one, sometimes there is a flash at the bottom. Or directly, if you remove this one, there is a sudden flash. That flash is due to the self-induction effect. Because a sudden current is going through this fan, constant current, suddenly you are changing. Means it will send the current in the opposite direction, then those electrons will collide and producing that flash. That is the effect of cellular. Wherever we stop some switch, at that point suddenly there is a flash sometimes at the bottom. So that is the self-induction effect. That we can see till date. But mutual induction is not very common nowadays. See how. variable resistor. There is another coil. There is a galvanometer. Okay. Now there is a current flowing through this. So a magnetic field will be developed. What is the value of this magnetic field? I first draw the magnetic field lines. The magnetic field lines will be look like this. See, current is flowing through this. So if you see from this portion, it looks anti-clock. So there is a north pole, there is a south pole, and field lines are passing inside the magnet through south to north. Draw these field lines. Now what happens? The field lines of the first circuit passes to the second circuit. Means there is a flux associated with the second circuit also. Field lines of the first circuit is passing through second circuit also. That means in the second circuit some flux is linked. Now if you change the current in the first circuit, then magnetic field of the first circuit will change. Not only that, magnetic field of the second circuit, flux of the second circuit will also change, because this magnetic flux field is B equal to mu naught L, and some field lines are passing through this second circuit. So if you change the current in this one, then this B will be affected, and once this B is affected, there is a change in the magnetic field with the second circuit also. So there is a change in flux with the second circuit. So if there is a change in flux with the second circuit, then an induced EMF will be developed in the second circuit, and due to this induced EMF, there is a current flowing through the second circuit. But Lenz's law is there. This current tries to oppose the change in the electrical state. So what it will do? It will try to oppose the cause of its production. So what is the cause of production of current in the second circuit? Change in current in the first circuit. So it will try to oppose the change in current in the first circuit. So it will interfere. That's why it is called mutual induction. So due to change in current in the first circuit, magnetic field associated with the second circuit will change. Due to that, a current is induced in the second circuit. But due to Lenz's law, this current tries to oppose the cause of its origin. Cause of its origin is the change in flux in the first circuit. So this current will induce an back EMF in the first circuit to restore the current in the first circuit to the constant value. So now previously it is stopping the change on its own. Now it tries to stop the change on the others. That's why the effect is called mutual inductance. So to prevent this, it is advised that two similar circuits or coils must be kept far away from each other. Otherwise, one's mutual induction will affect the other. Clear? So this is the mutual induction effect. Now we will discuss that if there is a coil there is a resistance and there is a cell. Supplying a current I. In the circuit. I deliberately write this one as small I. Then at any moment, if I write Kirchhoff's law, voltage law for this one, I can write it in this manner. Sorry. This one, because across the inductor coil the EMF developed, I have already derived this one now, minus L di dt. So I consider the magnitude only, that is L di dt, because minus L di dt means the back EMF. So plus L di dt is the EMF developed by the battery across the inductor coil.